Hey everyone, welcome back to the channel. Today, we're going to dive deep into some image processing and put three different techniques to the test. We're going to take a look at how we can convert images to grayscale and see how different languages handle the workload. We're going to use Kotlin, classic C++, and an optimized C++ method. And we're going to show you which one does it fastest. To get more consistent results, we'll be testing each implementation up to 10 times. Let's jump right into it. Here's the app we've built. It's a simple image processor, and as you can see, it loads a simple image. You can easily refresh to restart. We have two buttons, one known as native CPP and the other one known as KTX, which will stand for our Kotlin implementation. These buttons will apply a grayscale filter to the image and display how long it took to process. Let's test the native C++. There it is, our image in grayscale. And there's the time it took to transform the bitmap. Let's try the KTX version. There we have it as well. We get the same visual result, but what about the time? Let's discuss these results later on. And of course, if we click on the refresh button, we go back to the initial states. Let's start with the Kotlin implementation. In our activity file, we have a composable named grayscale screen, which is the main screen. This composable uses the image grayscaler component to display the original image, the processed image, and the time it took. The time is provided by the transform timer data class. This same component is used to showcase C++ and the optimized version. All you change is the parameters that are being passed. Let's look at the KTX to grayscale function. Here is our core image processing logic in Kotlin. We are using a color matrix to set the color saturation to 0. Effectively, this transforms all colors to shades of gray. This is achieved by creating a canvas and paint object to ultimately draw the bitmap using the new color settings. It's pretty straightforward. Now, let's move to the C++ side. We are using the NDK, short for the Native Development Kit. This allows us to write and compile C++ code that runs directly on the Android device. Our C++ code lives in the image filter.cpp file. In order for Gradle to properly build and package our native code, we must add the external native build configuration. To do that, we open our build.gradle.kts file. Inside the Android block, we declare the external build using CMake. Here, we provide the path to our CMake lists.txt and the version of CMake. This is key to be able to use our C++ code. Without it, our project would fail to build. It's being compiled as a shared library thanks to our CMake list.txt. This file allows us to link our library to the GNI graphics, which is necessary to work with bitmap. Let's now inspect the CMake file. It is a standard file for a C++ Android project. First, we set the minimum required CMake version. Then we declare the project name. After that, we use the add library function to create our shared library. This is the name of the library we need to use in order to load our C++ code into Kotlin. We also add our source files, in our case, our .cpp file. Finally, we use the target link libraries to specify the dependencies needed for our C++ project. In our case, the Android, log, and GNI graphics. The GNI graphics library is pretty much important for us to be able to handle Android bitmap operations. In our main activity file, we have our native functions and a static block to load our library using system.loadLibrary and then provide the name of the library. We have two functions, process to grayscale and process to grayscale optimal. Process to grayscale is our basic implementation, while process to grayscale optimal, as its name indicates, is a more optimized one. Both functions receive a bitmap object with Kotlin, The most important part of our C++ code is the locking and unlocking of pixels of the bitmap. The Android bitmap lock pixels function is crucial for allowing us to manipulate the bitmap pixels. The first function will convert the pixels one by one according to the grayscale formula. The optimized version is very similar, but we use integer math instead of floating point. We create a new bitmap and modify the pixels before giving back the new grayscale image. A full copy of the C++ code is available with the link of the repository in the description below. For now, you can get time, put this onto an AI and read out what it does and happens in here. I am not a very good C++ dev, but this kind of works to some extent. So, how does C++ talk to Kotlin? Because our app is written in Kotlin, and this function is written in C++. This is where the Java native interface comes into action, or in short, JNI. In our main activity Kotlin file, you can see we have functions declared as external. This indicates that these are implemented in a different platform, and in our case, C++. The names of the functions in C++ follow a specific naming pattern. There is the preceding Java underscore, followed by the package name, then the class name, and then the function name. This is how JNI knows which C++ function is the equivalent of the external function in Kotlin. By using this system, we are able to call C++ functions directly from Kotlin, making the transition between the languages seamless. Now that we know how both sides work, let's do a direct comparison. On the Kotlin side, we are working with high-level abstractions like color matrix and the canvas. This makes the code more readable and easy to understand. However, it does come at the cost of performance. The image processing is done on the canvas class. When using C++, on the other hand, we are now down in the trenches, directly manipulating the raw pixel data using the Android bitmap class. This gives us more control, which we can use to optimize our code. The raw pixel access makes the code a bit more complex, but is the key to faster processing. Let's look at the app again. Well, some interesting results there. In this case, we can see, even though both versions do get the same result, the C++ version at certain scenarios and situations is a tad faster than the Kotlin one. The optimized one will be even faster. However, it is important to note that not in every instance of our grayscaling operation does the Kotlin one lag behind. Sometimes it pulls up ahead, other times it does not. Let's look at the optimized version in this case. Here's how we kicked things up a notch. First, we moved away from the floating point math, which is slower, and used integer math instead. Grayscale calculation can be done just fine with integer. We also use a more efficient formula to make it even faster. We also made sure to create the new bitmap directly in C++. We are no longer processing in place, but giving back the new image. This made it even faster. These little tweaks might seem small, but they add up a significant improvement in performance. Let's see how our optimized version works within our app. Alright, let's get into the final results. To ensure we get consistent and reliable data, we ran each method 10 times and averaged the results. While running our test multiple times, we could see that the numbers were pretty consistent. After averaging them, we get a clear picture. As we've seen, Kotlin is great for rapid development and ease of use, but it's slower when it comes to raw image processing. Standard C++ gives us a massive speed boost because we are down at the pixel level. But when we apply our optimizations in C++, we hit the highest performance we can possibly. Here is a table showing the average execution times for each of the three methods. Now, what does this mean in the real world? If you're building an app where image processing is a core, or high performance operations are required, like a photo editor or a filter app, every millisecond counts. This is where C++ optimizations are vital. If you're just doing some simple image manipulations, Kotlin might be enough. It all depends on the type of app that you're building. Well, there you have it, folks. That's the end for today's video. A nice experiment that came into mind. How well can we optimize operations on Android? And writing native code is one of them. However, it can come with its own downsides because, one, you have to understand native code, which can sometimes be a bit difficult to do. Anyway, if you'd like more examples, more samples, more experiments on Android, the JNI, and some native code, don't forget to like, share, and subscribe.